Welcome to Ancient Earth, where every fossil tells a story and every bone holds a whisper from the deep past. Imagine a vast floodplain in the late Cretaceous. A towering Edmontosaurus, a type of duck-billed dinosaur, moves through a grove of conifers, its heavy footfall shaking the ground. You watch its powerful jaws strip bark from a tree, and you see the immense muscles of its body at work. We can learn so much from its skeleton. The strength of its legs, the complex grinding surfaces of its teeth, the size of its brain cavity. But bones only tell part of the story. They are the blueprint of the machine, but they don't always tell us how it ran, what fuel it used, or what it left in its wake. Ever wonder what it truly felt like to stand in the shadow of a living giant? To know not just its size, but its habits? The answers often lie in the clues left behind. Now, let's journey back in time and uncover the story of a lost world. To truly understand the life of that Edmontosaurus, we need more than its skeleton. We need evidence of its behavior. We need its tracks, its nests, and, believe it or not, we need its dung. It may not be the most glamorous subject in paleontology, but the study of fossilized feces provides one of the most direct and unfiltered windows into the daily lives of these incredible animals. These humble fossils tell us, with startling clarity, exactly what was on the menu in the Mesozoic, and the story they reveal is more fascinating than you could ever imagine. What we are talking about are trace fossils, evidence of an animal's activity rather than its body. And among the most informative of all are those known by the scientific name Coprolites. The term was coined in the 1822 by the brilliant and slightly eccentric English geologist William Buckland. It comes from two Greek words, kopros, meaning dung, and lithos, meaning stone. A coprolite is, quite literally, a dung stone. It is the fossilized excrement of an ancient animal, and its existence is something of a geological miracle. Think about it. Under normal circumstances, animal waste decays and disappears almost instantly. For it to become a fossil, a very specific and rare sequence of events must occur. First, the dung has to be buried incredibly quickly before it can be scattered by weather, eaten by scavengers, or decomposed by bacteria. The best places for this are aquatic environments. Imagine a dinosaur defecating on the edge of a lake or in a swamp. The waste sinks into the soft, oxygen-poor mud at the bottom. This anoxic environment slows decay to a crawl. Over millions of years, as more sediment builds up on top, the pressure increases. Water rich in minerals like silica or calcite percolates through the buried dung. Slowly, molecule by molecule, the original organic material is replaced by these stable minerals in a process called permineralization. The result is a rock that preserves the exact shape, size, and sometimes even the microscopic contents of the original dung. What was once soft and ephemeral becomes hard and permanent. A stony package of biological information, waiting for a paleontologist to slice it open and read the story of a meal eaten tens of millions of years ago. To appreciate the power of a coprolite, let's look at a truly spectacular example. Picture a fossil hunter in the Badlands of Saskatchewan, Canada. They come across a brownish, oblong rock, nearly 2 feet long and weighing over 15 pounds. Based on its immense size, and the geological formation it was found in. There is only one likely culprit for producing such a colossal dropping: Tyrannosaurus rex. This was the droppings of a tyrant king. But the real excitement began when this specimen was taken to the lab and carefully analyzed. A CT scan revealed its contents before it was even cut open. The scan showed that this was not the waste of a scavenger that was picking at scraps. This was the waste of a predator at the top of its game. The coprolite was densely packed with chunks of bone, making up 30 to 50% of its total volume. The bone fragments were from a juvenile herbivore, possibly a triceratops or a duck-billed dinosaur. This was direct evidence, the ultimate smoking gun, of what a T.rex ate. But it told scientists so much more. The bone fragments were not rounded or heavily etched by acid. They were sharp and angular, indicating they had passed through the dinosaur's digestive system relatively quickly. This suggests T.rex had a very rapid and powerful digestive process. Furthermore, the sheer amount of crushed bone confirms that its bite force was truly off the charts. It wasn't just biting off chunks of meat. It was pulverizing the skeletons of its victims, consuming bone and all, to extract every last bit of calcium and phosphate. This single, unglamorous fossil gives us a more visceral and detailed understanding of the T.rex's feeding behavior than a dozen skeletons ever could. It's a snapshot of its sheer destructive power. The story locked inside Coprolites isn't just about the hunters. It's equally revealing about the hunted. Understanding the diet of giant herbivores has always been a challenge. Because plants, especially the soft, leafy parts, rarely fossilize well. We can look at their teeth and make educated guesses, but a coprolite provides the hard data. Let's return to the world of the duck-billed hadrosaurs. These dinosaurs, with their sophisticated dental batteries capable of complex grinding, were clearly successful plant eaters. But what kind of plants? For years, they were imagined as gentle browsers, placidly munching on soft ferns and waterside vegetation. Coprolites have revealed a far grittier reality. When scientists slice open a hadrosaur coprolite and put it under a microscope, they find a treasure trove of botanical information. Yes, there are bits of fern, but there is also a surprising amount of pulverized wood. These dinosaurs weren't just nibbling leaves. They were actively browse on twigs, bark, and other tough, woody material that would have been rich in fiber. This completely changes our picture of their feeding strategy, suggesting they were highly adaptable foragers, capable of processing much tougher food than we gave them credit for. Some hadrosaur coprolites contain another surprise: high concentrations of rotted wood, teeming with the fossilized spores of fungi and the tiny tunnels of invertebrates. This has led to the fascinating theory that these herbivores may have deliberately sought out rotting logs. The decaying wood would have been pre-softened, and the fungi and bugs living inside would have provided a rich source of protein and other nutrients not readily available in fresh plants. The gentle, prehistoric cow is replaced by the image of a hardy, opportunistic forager, a master of getting the most out of its environment. A last meal is just the beginning of what a coprolite can reveal. By looking closer, scientists can uncover intimate details about a dinosaur's health, physiology, and even its social life. When you put a thin section of a coprolite under a high-powered microscope, you might find more than just undigested food. You might find stowaways. Paleontologists have identified the fossilized eggs of parasitic worms, such as nematodes and trematodes, locked inside the coprolites of both carnivores and herbivores. This is a stunning revelation. It tells us that dinosaurs, just like modern animals, suffered from internal parasites that lived in their digestive tracts. We can begin to study the paleopathology of these creatures, the diseases and ailments that afflicted them. This paints a much more complete and realistic picture of dinosaur life, not as idealized movie monsters, but as real animals that got sick, dealt with infections, and were part of a complex web of life that included even the smallest parasites. On a much larger scale, coprolites can hint at complex social behaviors. In certain locations in Montana and Argentina, paleontologists have discovered what can only be described as communal dinosaur latrines. These are massive bone beds, but instead of bones, they contain huge accumulations of thousands of herbivore coprolites, all deposited in the same area over a long period of time. This isn't random. This is organized. This behavior is seen today in animals like rhinos and elephants, which use communal dung heaps to mark territory, communicate with each other, and help with sanitation around feeding grounds. Finding this same behavior in the fossil record is powerful evidence that many herbivorous dinosaurs were not solitary wanderers, but highly social animals that lived in herds and coordinated their activities. From a microscopic parasite egg to a giant communal latrine, fossilized feces give us clues to a whole world of behavior that bones alone could never show us. While a single coprolite can tell you about a single animal, a collection of them from the same place can bring an entire ecosystem to life. Imagine you are a paleontologist excavating the fine-grained sediments of an ancient lakebed from the Cretaceous period. The site is a goldmine for trace fossils. You don't just find one coprolite. You find dozens of different shapes and sizes, all in the same geological layer. This is where the real detective work begins. You take them back to the lab and start to analyze the contents of each one, piecing together a prehistoric food web. A small, pellet-like coprolite is found to be packed with the shiny, iridescent wing cases of beetles. You have just found evidence of a small, insect-eating dinosaur, or perhaps an early mammal. Nearby, a larger, spiral-shaped coprolite, the shape suggestive of a fish's gut, is full of crushed fish scales and tiny vertebrae. You have just confirmed a fish eater was patrolling this lake. A third, medium-sized specimen contains fragments of hair and tiny mammal teeth, clear evidence of a small predator, maybe a dromaeosaur like Velociraptor, that hunted the fuzzy creatures living along the shore. And finally, you find a truly massive coprolite, the one containing the bones of a much larger plant-eating dinosaur. Now you have your apex predator. By analyzing the droppings of an entire community, you can move beyond simply listing the species that live there. You can start drawing lines between them, connecting the insects to the insectivore, the fish to the fisherman, the mammals to the raptor, and the herbivores to the tyrant king. The jumbled puzzle pieces of a lost world snap into place, revealing the intricate and dynamic flow of energy through an ancient environment. The study of coprolites, now a vital subfield of paleontology, began with skepticism and a few raised eyebrows. When William Buckland first began presenting his fossil fir cones and bezoar stones to the Geological Society of London in the 1822, arguing they were the fossilized feces of ichthyosaurs and other ancient reptiles, Many of his colleagues thought it was an undignified, if not downright comical, subject for serious scientific inquiry. Yet Buckland persisted, meticulously documenting their contents, like fish scales and bones, and proving their biological origin. He established a new frontier in the study of ancient life, even if it remained a niche curiosity for over a century. For decades, coprolites were mostly collected as oddities, interesting conversation pieces for museum shelves. The real revolution came with the advent of modern technology. The ability to create ultra-thin sections of these fossils allowed for detailed microscopic analysis, revealing the plant cuticles, pollen grains, and parasite eggs that had been invisible before. In recent years, scanning electron microscopes have given us even more powerful views of these microfossils. The use of high-resolution CT scanners has been a game-changer, allowing paleontologists to digitally dissect a rare coprolite layer by layer, exploring its contents in 3D without ever having to cut or damage the specimen. And now, paleoscientists are even pioneering chemical analysis, able to identify specific organic biomarkers preserved within the mineral matrix, potentially linking a coprolite directly to the species that produced it. The legacy of these humble dungstones is a testament to scientific persistence. They have been transformed from a geological curiosity into one of the richest sources of data about prehistoric life, proving that sometimes the most profound secrets are hidden in the most unlikely of places. The journey through the world of coprolites takes us from the grand scale of a T.rex's digestive power to the microscopic drama of a parasitic infection. It is a story that reminds us that the past is not silent. It speaks to us not just through the grandeur of a mounted skeleton, but in the subtle, often overlooked traces left behind. These dungstones, once dismissed as mere curiosities, have become invaluable chronicles of daily life in the Mesozoic. They provide an undeniable, direct link to the diets, behaviors, and diseases of animals that have been extinct for tens of millions of years. They are a profound reminder that every fossil, no matter how humble, holds a piece of the puzzle, and that there is still so much to learn from the whispers of ancient Earth.